Hello everyone, this is another video from Smart Vision Europe, and this time we're looking at the latest release of IBM SPSS statistics. That is version 27. And as with every new release of IBM SPSS statistics, there are a whole bunch of key changes and new functionality that have been introduced. One of the big things that's happened is that data preparation and bootstrapping are now part of standard functionality within SPSS. So that means that these were previously optional add-on modules. You had to purchase them separately. If you didn't have those modules in the past, you will now have them as part of your standard functionality. They're very powerful and very useful modules, so that's quite a big step. Power analysis has been introduced. We'll be walking you through an example of power analysis, what that is and how to apply it. Effect size statistics for t-test and one-way ANOVA. Also some optional display enhancements for bivariate correlations. The introduction of pre-built chart templates. If you're used to working with things like table looks, then chart templates work in the same way. You can simply have different formatting for charts, and IBM SPSS now comes with a bunch of pre-built chart templates that you can choose. There's the introduction of bubble plot charts, auto recovery facility, which allows you to recover work if the system crashes, and some enhancements to the search facility within the package. Before we get into looking at the new analytical functionality within SPSS, just to give you a reminder, an overview of what the bootstrapping module actually does. And bear in mind, of course, this is now going to be part of the standard package within SPSS. Bootstrapping is actually quite a well-known and established method that statisticians use to estimate statistical values and ensure that analytical models are reliable and accurate. Of course, the whole point about statistics, generally speaking, is to use samples to try and estimate a value that exists out there in the population. So you're always working with samples, and bootstrapping treats a data sample, as if it was the population, and it repeatedly resamples the data file. So it basically takes many subsamples from the data file and then creates overall estimates, if you like, of means and standard deviations and things like model coefficients. And you'll see that the bootstrapping button appears on dialog boxes within many different procedures in SPSS, including things like descriptives, the means procedure, crosstabs, correlations, and regression. So that's going to be part of the standard package going forward, as will the SPSS data preparation module. This is a really powerful module, very much a Swiss Army knife, that allows users to identify problems or errors in their data set so that they can prepare it before analysis. It uses a combination of basic checks, a series of rules, anomaly detection algorithm, and it generates both output reports that tell you, what the level of quality is with your data, but also new variables that help you identify problematic cases or unusual records. So the sorts of things you'd expect to be able to do with the data preparation module is to detect quality issues, define your own checking rules, identify duplicates. There's something called optimal binning, which is a kind of a smarter way to band numeric variables together. It also allows you to assess extremes and anomalies, and it does things like preparing date and time fields, or excluding low quality fields, or rescaling intervals, or filtering out poorly performing predictors that you might use in a predictive algorithm. In both the data preparation and the bootstrapping module, you should be aware that we have little videos on the Smart Vision Europe website that give you kind of a 2-minute overview of these. So you might want to check out our website if you're interested in getting a slightly more detail or an illustration of how these two new standard modules, which are now part of the base, how they actually work and what sort of output they produce. Okay, let's have a look at the new analysis functionality within IBM SPSS Statistics version 27. The first thing we're going to look at are effect size calculations. Now, you may be aware that in statistical analysis, it is actually possible to reject a null hypothesis, that is, in inverted commas, to find a statistically significant result when you're using a probability test like chi-square or t-test, even when the difference or the relationship that you're observing is quite small or quite weak. So it is possible to say this is statistically significant, but the difference is actually very small. So in order to measure the differences or to measure the strength of the relationship in a sort of standard way so that you can compare one t-test result, let's say, to another t-test result, statisticians use techniques like effect size. So effect size is used to measure the magnitude of the observed relationship in conjunction with a statistical test. And one of the most common effect size statistics that's used, for example, for comparing pairs of mean values is Cohen's d. And Cohen's d works by looking at the differences between the pair of mean values for group 1 and group 2, if you like. What is the difference between the averages? And it divides that difference by what it calls the pooled standard deviation, which is basically the weighted average of the two standard deviations. It basically takes an average of the two standard deviations for the two groups, taking into consideration, of course, the sample sizes, which is the weighted bit of it. And it divides the difference between the two means by this pooled standard deviation. So it's effectively a ratio, if you like, of the difference to the spread in the data. Now, generally speaking, most statisticians regard Cohen's d point estimates, or Cohen's d values of around 0.2, as quite small differences. It's a kind of standard scale, if you like. It says this is quite a small difference, whereas values around 0.5 would be regarded as quite medium-sized effects, and those above 0.8 as large effects. So they're almost like interpreting them in the same way that one would interpret a correlation value. Let's have a look at how that presents itself within SPSS. So this is version 27 of SPSS. You may notice right away that it looks slightly different from the previous version. That's because they've kind of introduced a new look and feel. If you go into the Edit Options General tab, you'll see that the look and feel is set to SPSS Lite by default. The old look and feel was SPSS Standard, which you can switch back to, as you can see here. Let's just switch back to the new look and feel, so we get used to that. SPSS Lite, hit apply, click OK. And if we wanted to illustrate, for example, an effect size, I'm going to run a t-test quickly here. So I'm just going to analyze down to compare means, and then look at a t-test, an independent samples t-test, where we'll compare gender. Let's look at F&M for female and male gender, and we'll look at average years of education. So if you look at average years of education, now you notice that estimate effect sizes is switched on here, so that's going to give us both the t-test result and the effect size. We click OK here, and the t-test result here is showing that it is statistically significant difference between the two means. You can see the means up here are 12.37 and 14.43. Not a vast difference, 2 years or thereabouts. And the Cohen's d effect size for that point estimate, it doesn't matter if it's negative or positive, it's because it's just the order in which the two values appear. So it's comparing male to female, and it's giving us a point estimate here of 0.763 or minus 0.763. So that's showing a reasonably strongish, if you like, effect. Let's have a look again at some of the new analytical procedures that have been introduced, and we can use t-tests here to further illustrate the application of power analysis. If you're not familiar with power analysis, it plays a key role for many researchers in the planning and design of research studies. So statistical tests, as we know, look for evidence that you can reject the null hypothesis and conclude that there is an actual effect or relationship in the population. But any statistical test, there's always a possibility that you will find a difference or an effect when in reality one does not exist, or what's known as a type 1 error. There's also the possibility, of course, that you will miss an effect because the sample size wasn't large enough or something like that. So that's a type 2 error. Statistical power calculates the probability that your data or analysis are sufficiently robust to detect the relationship in the first place. So it's basically telling you how strong your statistical test is, or how strong your study is, based upon the amount of data that you've collected and the variation in the number of groups you're trying to compare, etc., etc. It's generally accepted that just as with statistical tests, you have an alpha level of 0.05. That's the point at which you reject or accept a null hypothesis, or 5% level. In power analysis, it's generally accepted that the power value should be 0.8 or greater. In other words, you should have at least an 80% or greater chance of finding a statistically significant difference when there really is a statistically significant difference. And for this reason, power analysis is often used to calculate factors like required sample size prior to the data being collected. But you can also apply it post hoc. You can actually also say, I've done an analysis and now I want to see what is the power score for that analysis. So we can return to our earlier t-test and run a power analysis on our earlier t-test to see what the statistical power is associated with that output. So here's the output from our earlier t-test that we've just run, and we're going to use the information from this t-test to calculate what the statistical power is associated with this t-test. Now, I can tell from looking at it that you've got two quite large sample sizes here of 216 and 258 males. So you'd expect it to have quite strong statistical power, easily above the threshold of 0.8, especially as the standard deviations are quite small relative to the mean values. But let's go ahead and do that. If I go to Analyze, Power Analysis is now right at the top, and if I go to Means Independent Samples t-test, you can see that I can either ask it to estimate what sample size I would require in order to get a power value of 0.8, or I can ask it to estimate the power based upon some analysis that I've already done. What is the power associated with this? So I'm going to do that. I'm going to go estimate power. What is the power of this? And tell it what the sample size is for group 1. That's the females. 216, as we can see here. So it's 216 females and 258 males. I'm actually going to put in the population means, or the sample means, if you like, for the two groups, the assumed population means. 12.37 years of education for females, 14.43 years of education on average for males. And then we can either put in a pooled standard deviation, so we can calculate a pooled standard deviation, or we can put in, assuming that we're going to look at the equal variance is not assumed, which is correct here, we can put in the standard deviations for the two groups. So here we have quite small standard deviations for women, 2.319 in this sample, and for men it's 2.979. And as soon as I do that, the OK button is now activated. I can click OK and it will calculate the statistical power for me. And here's the power value as it comes out. It's coming out as 1, which makes it sound like there's a 100% chance that given these values, you should be able to detect an effect and reject a null hypothesis. That would normally be reported as greater than 0.999, if you like. So it doesn't necessarily mean it's absolutely 100%, but it's a very, very strong power value. If I go back actually and just rerun this again, let's say we reduced the sample size down to, let's say we only had 20 females and 20 males. What would the statistical power be in those situations? Click OK again. Well, now the power goes down to 0.661. So you can see that the sample size makes a big difference, as will the standard deviation. But that's how we can apply power analysis post hoc, if you like, after a test. But it also allows us to calculate, what sort of values we would need to be achieving, what sort of sample sizes we would need to be achieving in order to get the required statistical power. One of the best new enhancements for me personally that I like is the new correlations output options that I have. For many years it's bothered me that SPSS shows correlations twice, so basically it's always duplicated the correlations, unlike other software packages which generally only tend to show the lower triangle of the correlation. So you're not seeing the correlation between current salary here, for example, and education level twice over. You can only see it once, and you also have the option to tell it to show the diagonal, so you can show the 1 values down here if you like, or you can ask it to switch that off. So it's really only showing you the relevant information. We know that the correlation between, for example, beginning salary and beginning salary is 1, so we don't really need to see that, and we don't need to see the correlation between beginning salary here and say education level repeated twice within the matrix. So showing only the lower triangle is a nice enhancement. A few additional bits of functionality have been added to the chart builder dialog. So you can now, for example, build bubble plots. Bubble plots were only previously available through the GPL syntax. They are associated, of course, with scatter plots, where you're adding in a 4th field. So here we have current salary against beginning salary, colored by employment category, but where the size of the circles relates to the actual age of the employee, where larger circles mean that they're older employees. And also within the chart builder dialog, you can actually select a different chart template. There's a small sample of pre-built templates that you can choose, and again you can of course switch these so that they are a different template is used by default by going to edit options. Let's just have a quick look at this new functionality within the chart builder dialog. So to illustrate, if I just go to graphs, chart builder up here, and call up the dialog box, let's just build a bubble plot by going of course to scatter here, choosing scatter plot, and then we'll put in our variables, current salary against beginning salary, colored by employment category here, and where crucially the size of the circles, the size of the bubbles, varies according to the age of the employee. And over here on the right hand side, we've got this little tabbed set of functionality where we can go to chart appearance, something that was new, and we can say use installed chart template. If you click on that, here's the default style. We could go for bright, gives you a little preview of what they look like. Legacy, for example. Pastels, go for pastels. Publication gray, or web report. Let's go for web report and click OK at that point. And that generates our bubble plot for us, which is quite an attractive way to represent 4 variables in a scatter plot. It's worth noting that there are a couple of extra enhancements with regard to exporting high resolution charts. So when you go to export output within the output viewer window and you select non-graphics only from the type of document that you want to export, you get the option now to export the output as a production ready PostScript, which is .eps. That's a high resolution image format. And you can also select scalable vector graphics, which is a .svg format. In terms of improvement to the overall system itself, perhaps the most fundamental one is the introduction of auto recovery. So automatic recovery is designed to help you recover unsaved files and content in instances where the application is quit unexpectedly. And you can actually enable or disable this feature within edit options. You can change the time interval that it uses between saving the files and change the file location to a different folder where it's saving the auto recovered file. If you should actually experience the application quitting unexpectedly, when you relaunch SPSS statistics, you'll be presented with a statistics error report, which will allow you to enter information about your session prior to the unexpected exit, and that of course will be used to help improve the quality of the product going forward. But after leaving the exit report itself, or the error report itself, you're presented with an auto recovery dialog, and it will provide you with options for recovering the prior session data or deleting any saved session data. Something else that has changed within the overall system is an improvement in how search is conducted. So now the new search feature has been updated to provide results that don't just search, for example, the help files, but also the menu dialogues themselves, case studies, and syntax reference information. Finally, a few miscellaneous improvements include things like changes to privacy settings, which give users more options with regard to what information is shared with IBM during a particular session, as well as the introduction of an issue reporter dialog under the help menu. This dialog allows you to enter information if you have any issues, any crashes or problems when using the product. The information then, of course, is then used to improve the product. And lastly, just the ability to call up a request that crosstabs and frequency tables produce output that conforms to APA style guidelines, American Psychological Association style guidelines. Please be aware that there are many other materials, videos, blogs, and downloadable materials from our Smart Vision Europe website, and we also have a YouTube channel. If you are interested in finding out more about SPSS, it's a good place to start.